All right, welcome back, everybody. Today we're going to be doing section 6.1. So if you watched my lecture on section 4.2, where I said we were going to be doing section 6.2, I misspoke. 6.1 is what we're going to do next. And this is the section where we learn about the inverse trigonometric functions. 6.2 is a continuation of the content about the inverse trigonometric functions. But I decided to push that until after we do section 7.1 because I feel like most of the examples in that section are in section 6.2 are easier to do once you've had section 7.1. So we'll do that later. For now, let's get started with 6.1, and we're going to learn about the inverse sine, cosine, and tangent functions, but also we're going to learn about the other ones, the inverse cosecant, arcs, the inverse cosecant, the inverse secant, and the inverse, oh geez, I'm sorry, the inverse cosecant, the inverse secant, and the inverse cotangent functions. Yes, that's right. I'm sure I'll remember once I look at the list again. There we go. So first we need to talk about domains and ranges. Then we'll do the inverse sine function, cosine function, tangent function, cosecant function, secant function, and cotangent function. So the inverse of all of those things. Um, I will say this section is a little bit long, so you might want to settle in. You might want to take a break in the middle. That's okay. There's a lot to cover in just this one section, so bear with me, but I'll try to keep things brief if I can. All right, so first, remember that a function has to be one-to-one in order to be invertible. So we need that property to be true. But the thing is, the trigonometric functions are not one-to-one, and so they don't have inverses outright. They fail the horizontal line test, and they fail the horizontal line test pretty miserably, right? If you think about, for example, the sine function, well, if I try to draw a horizontal line through it, it hits the graph many times. In fact, it hits the graph infinitely many times. So outright, when you think about, for example, the sine function defined on the real line, it's not invertible that way. So what do we have to do? We can make them invertible by restricting their domain. And I mentioned this in the lecture for section 4.2, but we can talk about inverses of functions that aren't outright invertible if we can restrict their domain in a meaningful way. And so that's what we're going to do in this section. But I will give you this word of warning. In general, you have to be very careful and you have to give very careful consideration to the domains and ranges when inverse functions are involved. So just be cautious. Think about what are the inputs, what are the outputs, what are the domains, what are the ranges, because sometimes if you ignore those, problems will arise, as we'll see. So let's talk about the restrictions that we're going to implement first. So we are going to restrict the domains of sine, cosine, and tangent as follows. So we're going to restrict sine to the angles. Oops, sorry, these should all say thetas, my bad. This should be theta right here. I can change that later. Theta, theta, theta. There we go. Theta, oops, theta, theta. So for the sine function, what we're going to do is we're going to restrict our domain to angles that are within negative pi over 2 to pi over 2. So in terms of the unit circle, that's all the angles that are over here on the right-hand side of the circle, including pi over 2 and negative pi over 2. So remember, what is sine, right? Sine is vertical displacement. So if you pick a point on this curve, I'll go back to a black marker here. There we go. So if I pick a point, sine is the vertical distance here, the vertical displacement. So one of the nice things about this choice, as we're going to see in the next slide, I believe, is that we will be able to recover all the possible outputs of the sine function using this domain restriction. All right, so sine is going to be restricted to negative pi over 2 to pi over 2. For cosine, what we're going to do is we're going to restrict ourselves to the interval 0 to pi, including 0 and including pi. So if we want to be able to talk about inverse cosine, we have to restrict the cosine function to this domain. If we don't, we can't invert it, can't talk about inverse functions, and we're dead in the water. So we need to include this restriction. Then lastly, for the tangent function, we're again going to restrict ourselves to the right-hand side set of angles, but now we're not going to include negative pi over 2 or pi over 2. And that's frankly just because, remember, if you have a vertical line, then it has an undefined slope. So we can't talk about tangent of pi over 2, and we can't talk about tangent of negative pi over 2 because the function is just not defined there. All right, so these are the unit circle representations of the restrictions that we're going to have for our functions. So more specifically, we have this. Here's the sine function, and its restricted domain is negative pi over 2 to pi over 2, and its range is still negative 1 to 1. And then cosine, we have 0 to pi, negative 1 to 1. And then for tangent, we have negative pi over 2 to pi over 2 exclusive, and then the range is negative infinity to infinity. All right, now, one thing that's important to note here is that each value in the interval negative 1 to 1 is actually still hit with these restrictions on sine and cosine. And this is what we want. We want this because what that means is even though we have cut most of the domain of sine and cosine away, we can still achieve all of the possible outputs of those functions just on these intervals here, which is great because now we're not losing any information, and this is largely because of the periodicity of these functions, right? They're periodic, so they repeat. And as long as you restrict the domain to a point where you can get all those possible outputs, then everything's good. Everything's covered. The same thing for tangent. So even though we restrict tangent to be in the interval negative pi over 2 to pi over 2, exclusive, the range is still going to be negative infinity to infinity. So we're going to get all the possible slopes of these lines. So we've lost no information in terms of outputs, which is great. All right, so we have this. Since inverse functions invert the domain and the range, we have this setup here. So sine inverse, otherwise known as arc sine, has domain negative 1 to 1 inclusive and has range negative pi over 2 to pi over 2. So yeah, remember that inverse functions invert the domain and the range. They switch the domain and the range. So when we want to talk about the inverse sine function, the domain and the range are switched. Uh, I'll say this too. I put both of these symbols on here because these two symbols are interchangeable. And I have a note about them on the next slide. Yeah, on the next slide. But you can use either one of these symbols. They're acceptable everywhere. Sine inverse or arc sine, cosine inverse or arc cosine, tangent inverse or arc tangent. Arc tangent. Yeah, totally interchangeable symbols. I will use them interchangeably. Sometimes I prefer tangent inverse, sometimes I prefer arctangent. It really just depends. All right. So you might be asking yourself, why are these functions called arc dot dot dot? Well, the main reason is that the output of these functions is an angle. The output of these inverse trig functions is an angle. So that's the one takeaway that you need to like cement in your head, especially what's down here in the box, but I'll get to that in a second. When we work with the inverse trig functions, what we're doing is we're putting in an output of the original functions, and we're getting out an angle that would lead us there. But remember that we're using radians, right? We do all of our stuff in radians. And remember that radians are the lengths of circular arcs on the unit circle. So that's why they're actually called arc sine and arc cosine and arc tangent and arc cosecant and arc secant and arc cotangent. Because what it's giving you is it's giving you the length of that circular arc. It's giving you that angle in radians, which is really cool. So maybe now you might feel tempted to always call it arc sine, arc cosine, and so on. Um, so a lot of times students will tell me that they struggle with inverse functions. And what I try to do to get them through that struggle is they should always rephrase inverse functions in these terms. So when you look at a function like arc sine, like for example, if I said, oh, what's arc sine of 1? Right? The way that you answer that question is quite literally by saying this sentence in your head. or out loud, even out loud, right? So, what is arc sine of 1? That is the angle that has a sine value of 1. Hmm. What angle has a sine value of 1? Think about it for a minute. What angle has a sine value of 1? Hmm. What could it be? It's pi over 2, right? It's going to be pi over 2. Pi over 2. Oops. It's kind of a funky looking pi. Here we go. There you go. It's pi over 2. How did I figure that out? Well, I imagined the unit circle and I said this sentence out loud to myself. What angle has a sine of 1? And then you think about the unit circle and you think when the sine value is going to be 1 and you say, oh, it's angle pi over 2, right? Yeah, so that's what it is. Ask yourself that question, this question that's in the box that I circled, that I'm pointing at. Memorize that sentence, say that to yourself whenever you're trying to do anything involving inverse trig functions, and frankly, just inverse functions, period. um, okay, so let's focus on the inverse sine function for a bit. So how do we define it? Well, the inverse sine function, or the arc sine function, is defined as y equals sine inverse of x, or arc sine of x, if and only if x equals sine of y. One thing that I will say, or yeah, one thing I'll say here is don't don't let the x's and y's throw you off or confuse you. You always want to just think of things in terms of inputs and outputs. Remember that these letters, x and y, they're totally arbitrary. They don't have to be x's, they don't have to be y's. They could be s's, they could be t's, they could be smiley faces, they could be laughing emojis. Like those symbols can be anything. It doesn't matter that one says x and one says y. All that matters is the relationship between those symbols related by the functions sine and arcsine. That's all that matters. So what is arcsine of x? Well, arcsine of x is going to be the angle whose sine is x. And that's what it is. So when you're, like we just did a moment ago, right? When you're trying to evaluate arcsine, you just say, what angle has this sine value? The sine value that I'm using as an input, right? Okay, so notice here, the inputs of these functions are the outputs of the original functions. And so what these inverse functions tell us is the angles that would lead us to those outputs. All right, let's look at a picture here. So this is a graph of the sine curve as it's defined on the whole real line. And again, it totally fails the horizontal line test, and you can see it. You can see it because if you, oops, if you draw a horizontal line, it's going to intersect the graph many, many times. So we needed that restricted domain. And that's actually what's pictured right here. So this is the restricted part of the sine function that we're going to use to be able to define the inverses. So here it is pulled out, and now we can look at it more directly. So if we want to be able to talk about arcsine or inverse sine, then we must only consider this part of the sine function from negative pi over 2 to pi over 2 inclusive, inclusive. And if you remember how to graph inverse functions, the graph of an inverse function is the graph of the original function flipped about the line y equals x. So this is what arcsine looks like. Let me highlight it here. There we go. I highlighted it in orange right there. So that's the graph of arcsine. That is like if you wanted to actually draw the picture of it, that's what the picture looks like, and that's it. That's it. That's the whole graph right there. How do you get it? Well, you take the graph of sine, which is right here, and you flip it around the diagonal, and then you get the graph of arcsine. All right. Now let's try an example here. So let's do a couple of these, and I want you to try it on your own, and I want you to try saying that phrase out loud. Just a reminder, since we're working with arcsine, this is the phrase. Let me erase this other stuff. Yeah, that's the phrase. So for this next example, this is what I want you to say out loud to yourself when you're trying to work on this problem. All right, so let's do the first one. Let's find the exact value of sine inverse of 1, and then sine inverse of negative 1/2, and then arc sine of square root 3 over 2. So think about it for a minute, say it out loud, and try it on your own. All right, now let's do it together. The first one we actually already did. What is sine inverse of 1? That's the angle in negative pi over 2 to pi over 2, whose sine is 1. So in other words, it's the angle theta, such that sine of theta equals 1. Well, since sine is vertical displacement, you imagine the unit circle and you think about where that vertical displacement is going to be 1, and then you can clearly see that it's going to be pi over 2. That's the angle that will give you a sine value of 1. So arc sine of 1 is pi over 2. What about the next one? What's arc sine of negative 1/2? Well, arc sine of negative 1/2 is the angle whose sine is negative 1/2. The angle such that sine of theta is 1/2. So how do you do this? Well, you imagine the unit circle again, right? Here's the unit circle. And I need the sine value to be negative 1/2. So it's a negative angle. The displacement is 1/2. So we get the short leg here. And what's that angle going to be? That angle is going to be negative pi over 6. And so that's our answer. Our answer is negative pi over 6 because sine of negative pi over 6 is equal to negative 1/2. There we go. And that's pretty much it. All right, now let's do the last one. What's arc sine of root 3 over 2? Well, it's the angle whose sine is root 3 over 2. So what is an angle within our restricted domain that has a sine value of root 3 over 2? So what do? You imagine the unit circle, right? You think about the unit circle, and you say, okay, I need the sine value to be root 3 over 2. Root 3 over 2 is the long leg, so it's going to look like this. And so that tells us the angle is going to be pi over 3. And voila, there it is. Oh, I'm sorry. I realize I have a typo here. This should be positive, so scratch that little bit out there. I'll fix that later. Scratch that bit out. Positive root 3 over 2. And you can think about it. If you want an extra exercise, what would be arc sine of negative root 3 over 2? You can probably figure that one out in just a couple minutes. All right, so let's talk about the cancellation equations. So one of the things that I mentioned in that lecture 4.2 is the cancellation equations. Everybody loves these. This is one of the things that we use these inverse functions for. But if you do the inverse, if you do sine of a, if you do sine of a value and then you take the arc sine of that value, you're going to end up with where you started with the original input. And vice versa. If you do sine inverse of x and then you do sine of that, you're going to end up with x again. So in essence, arc sine and sine cancel each other out, but it's not quite that way. So that's why I have this important note, this important note down here. When you're evaluating these expressions, it is very important to pay careful attention to the domains and the ranges of the functions involved, because the cancellation will not always work out the way that you expect it to. So you're not always going to end up with X. What I mean is you're not always going to end up with the same thing that you started with, because the domains that we restricted things to play an important role. We'll see in just a minute here. Okay, so let's try this one. Try to do this one on your own. I want you to think about it. Think about it on your own, and then I want you to say some stuff out loud, and we'll do it together in just a minute. All right. Okay. So now let's try to do it together. And first, I'm just going to try to make sense of what this is even asking. Like, what is this even asking me? So this is saying find the exact value of sine inverse of sine of pi over 8. Sine of pi over 8. Now, the first thing I notice is pi over 8 is not one of the standard angles that we know. So what is sine of pi over 8? Well, I know that that's going to be some weird irrational number, but I know it's not going to be like root 3 over 2 or 1/2 or root 2 over 2 or 1 or 0. It's not going to be any of those. So if I wanted to see what this is, I'd either have to use some sort of formula like we'll learn later in the course, or I would have to use a decimal approximation from a calculator. But that doesn't mean that I can't solve this, or doesn't mean that I can't compute the exact value of this expression. Because what we're doing here is we're doing sine inverse of sine of pi over 8. So we're going to look at the vertical displacement that you would get for sine of pi over 8, and then we're going to see what the angle would be that would give you that. But the angle has to be within the restricted domain. So let's take a look at this. Oh yeah, there we go. I just cut right to it. So pi over 8 is within our restricted domain, negative pi over 2 to pi over 2. So that means that the cancellation equations apply. They apply outright. These things cancel each other out, and you're left with pi over 8. There you go. All right, now let's try something a little bit trickier. Here we go. So try to do this one on your own. Give it some extra pause, and then we'll do it together in just a moment. All right, let's try to do it together. What is sine of 5 pi over 8? Well, that's another one where it's not a standard angle, so I don't have an immediate answer to that. But the other thing is that 5 pi over 8, I can kind of visualize where that is, right? Let me do this. Let me draw the unit circle. Let's see, 5 pi over 8, that's 5/8 of a pi. So 5/8 of a pi is probably going to be like around here. Just a random guess. Because if I were to cut this into 4 pieces like so, that would be 5 of them. Oops, just erased it. There we go. So this angle right here is 5 pi over 8. And so I can see that there is a sine value there. But here's the catch. I can't apply the cancellation equations because 5 pi over 8 is not in the interval negative pi over 2 to pi over 2. So this thing is not going to be equal, to 5 pi over 8. It's not going to be equal to that. But we can still evaluate this because remember, sine of 5 pi over 8, this piece, is just the vertical displacement, right? It's the vertical displacement that you get when you trace out that angle, 5 pi over 8. But there's an equivalent vertical displacement that does correspond to an angle that lies within our restricted domain. And I'm going to draw the picture right here. And then I have a better one on the next slide. But we can look at this angle instead. Sorry, it's a rough sketch, a rough sketch. But look, this vertical displacement is the same. Let me point here. This vertical displacement is the same as this vertical displacement. That really just has to do with the way that sine is defined and the symmetry involved with sine, right? So what is this angle here? Well, this angle is going to be 3 pi over 8, or 3/8 of a pi. So let me go to the better picture and we can make more sense of it. Yeah, so this picture is much nicer, but you can see that this angle right here is 5 pi over 8. And that gives us this vertical displacement, but that vertical displacement is identical to this vertical displacement right here, and this angle is the angle 3 pi over 8. 3 pi over 8. So we have this result. More specifically, sine of 5 pi over 8 is equal to sine of 3 pi over 8. And now that we're looking at sine of 3 pi over 8, 3 pi over 8 is within our restricted domain. So we can actually apply the cancellation equations, and we'll see that this is going to be 3 pi over 8. There we go. So it's a little bit funky at first to try to get used to what's going on here. And the other thing I want to point out is I'm not saying that 5 pi over 8 is equal to 3 pi over 8. I'm not saying that those two angles are equal. What I'm saying is the vertical displacement, the vertical displacement for those two angles is the same. And vertical displacement is sine. So it's not that the angles are the same, it's that the output of those two angles under the sine function is the same. So written out nice and clean here, we get that sine inverse of sine of 5 pi over 8 is equal to sine inverse of sine 3 pi over 8. And now we can apply the cancellation equations and we get 3 pi over 8. There we go. We're going to do another couple examples like this as well, because it does take some time to get used to it. My best advice right now is remember the unit circle. Everything goes back to the unit circle over and over again. It's always like imagining the unit circle, remembering what sine is, remembering what cosine is, remembering what the angles are, the standard angles, and everything just comes out of that. There's surprisingly very little calculation that's going on here. It's more just interpreting the unit circle. All right, so now let's move on to cosine. The inverse cosine function, or arc cosine function, is defined in this way. We say y is equal to arc cosine of x if and only if x is equal to cosine of y. More intuitively, if you want to work with arc cosine, this is how it's defined. Arc cosine of x is the angle whose cosine is x. So just like before, except now we're doing cosine. All right, let's look at the graph. Once again, outright, the cosine function is not invertible. It's not invertible, it doesn't pass the horizontal line test, so we needed to restrict the domain. And when we restricted the domain, we got this. Here we go. Here's what it looks like when you peel everything away. And that's the graph of cosine on our restricted domain from 0 to pi, right? 0 to pi inclusive. So what does the graph of arc cosine look like? Well, I think it looks a lot more fun than the sine function, or than arc sine, I'll say. But how do you get it? You're just going to reflect it about the line y equals x. And when you reflect that about the line y equals x, you get this. So this is the graph of arc cosine. There you go. So you can look at it for a minute, ponder it for a bit. Looks a little funky, but that is what the graph is. That is the graph of arc cosine. All right, now let's try some examples. The flavor of these examples is identical to what we saw previously. If you want to be able to do problems involving arc cosine, you just have to ask yourself, what is the angle that has this cosine value? So think about this one on your own, say that phrase out loud, and then we'll do this together in just a moment. All right, now let's do it together. What is arc cosine of 0? Well, that's the angle whose cosine is 0. What angle has a cosine of 0? I got to think about it. Okay, let me draw the unit circle. The cosine, or cosine is horizontal displacement, right? So what angle has 0 horizontal displacement? Oh, it's going to be pi over 2. There we go. So right off the bat, I can see that arc cosine of 0 is going to be pi over 2. Why is that? Specifically because cosine of pi over 2 is 0. So there we go. There's the answer. Now let's try to do the other one. What is arc cosine of negative root 2 over 2? That is the angle whose cosine is negative root 2 over 2. Let's try to draw a picture of that angle. Here's the unit circle. Negative root 2 over 2, that's one of those diagonals, right? That's one of the standard values. And it's negative, so the angle is going to go down. And this is the angle we're looking for, right? But since it's going to be negative root 2 over 2, we're looking at the horizontal displacement here, right? Cosine is, this is negative, sorry, I apologize. I'm thinking of vertical displacement. See, this is why you got to draw the unit circle each time. We're looking at horizontal displacement. So when is the cosine value going to be negative root 2 over 2? When it's over here. Oops, not the eraser. Come back. There we go. Right, so this value right here is negative root 2 over 2, and this angle right here is going to be what? Oof, 3/4 of a pi. So 3 pi over 4. Yeah, 3/4 pi. And that's what it is. So what is arc cosine of negative root 2 over 2? It's 3 pi over 4. Oh, there we go. 3 pi over 4. And that's the idea. Yeah, I mean, that's pretty much it. So once again, there's actually very little calculation. There's not really any algebra that you're doing. You're just thinking about the unit circle, thinking about where these values lie in terms of sines and cosines and tangents and such, and then asking what angle would lead you there. What angle would lead you there? All right, next, just like with the sine function, there are cancellation equations for cosine, but the catch is that those angles have to be within the restricted domain. So if you want to be able to apply this result, your angle has to lie in the interval 0 to pi. And if it doesn't, you cannot apply that result. And so that's why I was saying earlier that sometimes this value will not just be x again. It won't just be x again. It really, really depends on what the angle is and where that angle lies. So let's try this example. What's the exact value of cosine inverse of cosine pi over 12? Uh, Try this one on your own. Think about it, say it out loud, say that phrase out loud, and see if you can figure it out. All right, let's do this one together. Let's see, pi over 12, that is not one of those standard angles, so I don't know what cosine of pi over 12 is outright. I couldn't just say, oh, cosine of pi over 12 is blah, 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 blah. All I know is that it's cosine of pi over 12. But what I do know is that pi over 12 is in our restricted domain. It is in our restricted domain. So that means that I can apply the cancellation equations. These are going to quote unquote cancel, and so we'll be left with pi over 12. There it is. All right, so it's nice. It's nice when the angles are in just the right place. But let's mess things up a little bit here. Let's try this one. Or I want you to try this one on your own at home, and then we'll do it together in just a minute. Remember to say the phrase out loud. All right, let's try it together. Let's see, cosine of negative 2 pi over 3. 2 pi over 3, that is one of the standard angles. So maybe I can compute this in my head, right? Okay, so cosine of negative 2 pi over 3. Oh, what is that? That's going to be negative. Oh, see, I have to draw the picture. Negative 2 pi over 3 is over here, right? Over here. So cosine is going to be negative 1/2, right? Negative 1/2. That's what it is. That's what it is. There we go. There we go. Okay, so then what is an angle that has a cosine of negative 1/2? Well, we know that negative 2 pi over 3 does, so maybe that's the answer. But wait, that's not the answer. That's not the answer because negative 2 pi over 3 does not lie in the restricted domain. It doesn't lie in the interval 0 to pi. So the cancellation equation cannot be applied here. We can't apply it. So what we have to do is we have to think about the unit circle and we have to think about the restricted domain. And then we have to think about what angle in our restricted domain is going to have a cosine of negative 1/2. And if you look at the picture I've got down here, it's going to be right here. There you go. I'll try to draw it like so. It's this angle, right? So instead of going down this way, we have to go up this way because this is how we restricted cosine, right? We restricted cosine to the upper half of the unit circle. And what's this angle? This angle is actually 2 pi over 3. So that means that this expression here, the exact value of arc cosine of negative 2 pi over 3, is actually 2 pi over 3, positive. Yeah, there we go. There's the final answer. Here, I'll go back for just a minute here. This was essentially what we were figuring out with the unit circle picture I drew. Cosine of negative 2 pi over 3 is equal to cosine of 2 pi over 3, right? So we can essentially replace cosine of negative 2 pi over 3 with cosine of 2 pi over 3, and then we can apply the cancellation equation. All right. Okay, so that's it for arc cosine or inverse cosine. Now let's move on to the inverse tangent function. So we're about almost halfway through. What's the inverse tangent function or the arc tangent function? Arctangent is defined as y equals arctan of x, if and only if x equals tangent of y. Tangent of y. And, oh, I realize I have another typo here. Yikes. So maybe you can pick it out before I get to it. We need our x values to lie in the real numbers, but we need our y values to lie in this interval, but these should be parentheses. These should be parentheses. Why is that? Well, we can't do tangent of pi over 2. It's undefined there, so that's a typo. That's an error. Those should be parentheses, not brackets. But again, what's the intuition for arctangent? How do you actually compute the arctangent of something? This phrase. You say this phrase out loud. Arctangent of x is the angle whose tangent is x. Then you got to think about the restricted domain. Then you got to think about that. Okay, so let's take a look at this. Here's the graph of the tangent function itself. Remember, tangent is not invertible outright. It does not pass the horizontal line test. So that's why we had to restrict the domain. How do we restrict the domain? We're going to restrict it to the region negative pi over 2 to pi over 2. Exclusive. Just want to emphasize that again, that it's exclusive. There you go. And this is all we need because, again, we'll get all of the possible outputs from negative infinity to infinity, exclusive, as long as we just look at this part of the graph. I realize I didn't say it earlier, but I should say it now. The choices of restriction that we have are somewhat arbitrary. What that means is, tangent is a good example. It's easier to see. There's no law that says that we must restrict to this region in here. There's no like law that says we have to do it that way. It's really just a convention to make things easier on us. We could have just as well chosen this restriction instead. We could have said, oh, why don't we pick this interval instead? And just look at the tangent function on the interval negative 5 pi over 2 to negative 3 pi over 2. And all of the results we have would follow. We would still get the outputs. Everything would essentially be the same. The only difference is that we have to think carefully about where the angles lie when we try to apply the cancellation equations and when we try to evaluate these arctangents and so on. So just to keep things simple, we, as in like the mathematical community, decided let's just pick the one that seems the most straightforward, negative pi over 2 to pi over 2. And then for cosine, it was 0 to pi, right? Okay, so if this is what the tangent function looks like on its restricted domain, if we want to see what the graph of arctangent looks like, we reflect it over the line y equals x. Let me get my black pen here, right? Reflect it over the line, y equals x, and we'll get this. There we go. And there are still asymptotes. So what's nice about this function, there are still asymptotes at pi over 2. Let me make that a little darker. And negative pi over 2. So arctangent is bounded. And I have this really, really important note. So when you get to Calc 2 in particular, just remember, we really, really like arctangent. And we really, really like cosine. And we really, really like sine because they are bounded. They are bounded functions. So arctangent is bounded too. Arctangent is bounded between negative pi over 2 and pi over 2. That's what this picture is showing right here, right? And it's a little bit hard to get into, but the reason that we like these functions because they're bounded is because they don't blow up anywhere. They don't get too big. They kind of stay roughly, I mean, they do stay exactly within this range, negative pi over 2 to pi over 2 for arctangent, and then negative 1 to 1 for sine and cosine. And that helps out a lot, because when functions blow up to infinity or when they get very large, it can cause some problems. So we like bounded functions. They're always very nice. Okay, let's try this one. So let's find the exact value of arctangent of 1 and arctangent of negative root 3. Try this one on your own. Remember to say the phrase in your head and say the phrase out loud, and then we'll do it together in just a moment. All right, let's do it together. What is arctangent of 1? That is the angle that has a tangent of 1. All right, what angle has a tangent of 1? Tan theta equals 1 implies theta equals what? Well, remember, tangent is just the slope of that ray. the slope of that line, right? So if the slope is 1, then we saw earlier that that means the angle has to be pi over 4. The angle is going to be pi over 4. So that tells us that arctangent of 1 is pi over 4. Boop, there it is. Not too bad, right? Now let's try to do the other one. Arctangent of negative square root of 3. This one's a little bit weirder because I'm like, well, negative square root of 3. What angle has a tangent of negative square root of 3? Well, this is where those standard angles come in handy, and this is where the definition of tangent comes in handy, because tangent is just sine over cosine, right? So uh, this is often what you'll have to do for a problem like this. We can rewrite negative root 3 as negative root 3 over 2 over 1/2. Let me use the highlighter for that, actually, right? The 2's in those denominators will cancel, and you'd be left with negative root 3. You might even want to think about it as negative root 3 over 1, for example. Well, negative root 3 over 2 is sine of negative pi over 3, and 1/2 is cosine of negative pi over 3. But sine over cosine is tangent, and so what we get through this equation, this string of equalities, is that negative root 3 is tangent of negative pi over 3, just like so. There we go. So, well, if tangent of negative pi over 3 is negative root 3, then that means that arctangent of negative root 3 is negative pi over 3. There it is. So one thing I want to re-emphasize here is that to compute these things, you really are just thinking of the stuff you already know. You're thinking, what is tangent? What is sine? What is cosine? You're thinking about the unit circle. You're thinking about these angles and the standard angles. So it really does build on everything you already know. Not as much calculation as you might expect. There is one little subtle point I'll point out for this question, which is this. Remember the restricted domain. Oh, see, there's another one. Oh, I got to go through and fix these. I apologize. Those should be parentheses. Those should be parentheses. We need an angle between negative pi over 2 and pi over 2 that has this tangent value. And that's actually why I had to choose negative pi over 3, right? Negative pi over 3. If the tangent is negative root 3, think about the unit circle. Draw a little sketch of it here. Remember, tangent is just the slope. So if the slope is negative root 3, it's going to look the line is going to look something like this, right? So you might be tempted to say that, oh, it's this angle right here. But wait, that angle does not lie in this interval. So we can't use that angle. We must use this angle instead. And what is this angle? Negative pi over 3. So that's why you're essentially forced to pick that. And that was by design. That's by design. That's why we restricted the domain. I mean, that's because we restricted the domain. All right. Just like before. You see, now I sound like a broken record. Oh, man, I have some bad copy pasting errors here. I apologize. These should be parentheses. I'll fix those in the slides right after this. But again, we have cancellation equations for tangent. You just have to be very, very cognizant of what's the input, what's the output. Do these values lie within our restricted domain or do they not? And that's what you have to do. All right. So, okay, yeah. So since we've done a bunch of examples like this already, I'll leave you to do some on your own if you would like. The book has many, many more if you would like to try that. You will get to try many of them on your homework as well. But again, the main thing I can say is just say those phrases out loud. So for tangent, it was, where'd it go? This one, right? Arctangent is the angle whose tangent is x. Where's cosine? Come here, cosine. There you go. Arc cosine is the angle whose cosine is x. And then all the way back here, arc sine is the angle whose sine is x. And that's how you do all these types of problems. Okay, so let me get back to the bottom here. We're actually nearly done. We're nearly done. So there are 3 other inverse trig functions. There's the inverse cosecant, the inverse secant, and the inverse cotangent. But they're pretty much the same thing. They're pretty much the same process that we just did. So I didn't include any other examples. I think you'll be able to do these ones on your own. We'll just go through the definitions here. The inverse cosecant function, or arcsecant, is defined as y equals arc cosecant if and only if x equals cosecant of y. Now, you just have to remember what the restriction is. So here is going to be our restricted domain for cosecant, negative pi over 2 to pi over 2, inclusive, but we're also going to cut out the point 0. Going to cut out the point 0. And again, that's because you can't, I mean, not really, you can't take the cosecant of 0 because you'll get an undefined value. You'll just get no value because it's undefined. But notice that that choice of restricted domain is basically the same one that we had for sine, right? So remember, the restricted domain for sine was negative pi over 2 to pi over 2. So the restricted domain for cosecant is also going to be negative pi over 2 to pi over 2, with the additional restriction can't be 0. So we're cutting out the angle 0. And how do you answer these questions intuitively? The same way we've been doing. You say, well, arcsecant, geez, arc cosecant, oh man, arc cosecant is the angle whose cosecant is x. And you just work it backward. All right. Similarly, for the secant function, everything is the same idea again. So y equals arc secant of x if and only if x equals secant of y. What's the restriction? The restriction is the same as it is for cosine, except we also have to cut out pi over 2. Have to cut out pi over 2. And then how do you answer these types of questions? You say this out loud to yourself. You say, arcsecant is the angle whose secant is x. And you work it out that way. And then last but not least, arc cotangent, or the inverse cotangent function. How do you define it? Y equals arc cotangent of x means x equals cotangent of y. And then this one is a little bit different. So for this one, well, before I get to that, the domain is restricted a little bit differently. It's restricted to 0 to pi, 0 to pi. But how you answer these questions intuitively is just this again. Arc cotangent of x is the angle whose cotangent is x. So seems a little bit funky, but that's it. So what I recommend now, go try to do the homework, just working with these inverse functions. Try those examples. You can read more about them in the book if you would like. And then, like I had mentioned before, the next section, 6.2, I'm actually pushing to later in the course. So that's going to occur after we do section 7.1, because those problems will be easier to answer once we have section 7.1. But on that note, that's it. Goodbye, everybody, and I'll see you again next time.